have led to novel methods compatible with large-scale manufacturing. She's also a founder, an entrepreneur, and the chief scientific officer of Porosity Technologies, a university spin-out company supporting her group's research on porous nitrides and developing novel red micro-LEDs. Rachel is a passionate advocate for increased equality, diversity, and inclusion in science and engineering, and is a leader and founding member of the Inclusion Group for Equity in Research in STEM, the Tigers. She's an equality and diversity champion for the University of Cambridge School of Political Sciences and has addressed the parliamentary on scientific and equity issues. And on that note, I do want to extend a high five virtually to her for her recent leadership in responding to comments made in Parliament by Ms. Catherine Singh, chair of the Social Mobility Committee, stating that in the UK, physics is not something that girls tend to fancy. Rachel, thank you for contesting these assertions and providing evidence of structural and societal barriers which exist for girls entering the physical sciences. So without further ado, I would like to leave the floor to you for this wonderful talk that we are about to have. Thank you, Rachel.
Thank you very much. Can everybody see me and hear me okay? If somebody could say yes, that'd be lovely.
Loud and clear.
Brilliant. Thank you very much. So hi, I'm Rachel. Lovely to be speaking to you today. So I am in a very sunny Cambridge. It's hot and lovely here in the UK at the moment, and we're enjoying some nice weather. And I'm really glad to have the opportunity to speak to you about some of the work we've been doing in my research group about porous nitrides. And I'm going to particularly focus on how we're using those porous nitrides in light emitting devices. Minute, if I can make this thing go forward. There have been tons of people involved in this work across several years, particularly in my group in Cambridge, and I hope you can see all their names on the screen. Tong Tong Zhu, who was until fairly recently my postdoc and is now CEO of our spin-out company Porotech, is really a key person in that list. I'm also going to be showing work from some collaborators, including the group of Mark Holmes at the University of Tokyo and the group of Robert Taylor at the University of Oxford. And really very grateful to the great team of people I get to work with. Okay, so this is going to be a talk about gallium nitride, and I suspect that lots of people here are familiar with the gallium nitride material system. But before I get into our kind of weird and wonderful version of gallium nitride where we introduce porosity into this material, I'm just going to sort of remind everybody about why nitrides are an exciting material system to work with, and also give you a little bit of the underlying material science background. So the thing that nitrides are perhaps famous for is the blue light emitting diode, or LED. That's the device that underpins energy efficient light bulbs, which are a kind of important global energy saving technology. But there's loads of other nitride technologies as well. Nitride laser diodes. I'm very interested in single photon sources, although that's much more a lab-based technology than something that's out there for sale in the real world at the moment, but a developing research area. And then moving from optoelectronics towards electronics, there's a huge amount of focus at the moment on nitrides for electronic devices, largely devices for handling high powers or radio frequency signals. And all of these devices tend to start with nitride materials that are grown as epitaxial layers on foreign substrates. So rather than starting with a great big wafer of gallium nitride that is a bulk wafer, we start off with something else. It would typically be sapphire, silicon, or silicon carbide. And we use that as our starting point to then grow layers of gallium nitride on top that we then use to make our devices. And it's worth noticing in this picture, this is a transmission electron microscopy picture of a gallium nitride layer, that it's full of defects. There's lots and lots of mistakes in these crystals. They're very imperfect, but nonetheless, they're really useful for making the devices that I've talked about. Other things you might want to know about the nitrides. Well, this is a really marvelous material system because of the range of band gaps it can achieve. By alloying gallium nitride with indium nitride, we can move from the near UV into the infrared range straight through the visible. Alloying gallium nitride with aluminium nitride, we get out to the deep UV. So these are materials that give us an opportunity to work across the range of available wavelengths that we might want to work with. these are unusual materials, perhaps in their crystal structure. This is a hexagonal crystal structure material. That makes a difference to the performance of the material because this is a polar crystal structure, and that leads to internal electric fields and changes in the performance of the device. However, the nitrides, although they are a little bit different and maybe more familiar, arsenides and phosphides, these other kind of 3-5 semiconductors, have been hugely successful in making devices. Now, we're used to thinking about gallium nitride as a kind of monolithic material, these sort of nice solid layers of stuff, but we started to think about where else we could get ideas from to really be able to manipulate the properties of gallium nitride. And one of the things we learned about was porous silicon. So silicon is a material with an indirect band gap, but if you introduce porosity into it, it can become a light emitting material because you can change the way that electrons and holes behave in that material via creating this porous nanostructure. And this sort of porosity that I'm looking at here is often achieved by electrochemical etching, often with hydrofluoric acid. And you can achieve lots of different morphologies by tuning the etching parameters. And when these sort of porous nanostructures were first introduced, people were very excited about what could be achieved in terms of light emitters in these porous silicon materials. And excitement about that perhaps died down a little bit because this porous silicon is not very stable to oxidation. So porous silicon and porous silica, porous silicon dioxide, is still really in use today, in many sensing applications, for example, but it hasn't really been seen in light emitting devices. So it's an interesting question to ask, what can we do with porosity in a material that's already direct band gap and that's like a bit of a classic now for light emitting devices? So now we come to gallium nitride then as our light emitting material. And if we think the problem with porous silicon for light emitters was its instability to oxidation, we're looking in gallium nitride at a material that's much more stable to oxidation. We're looking at a material which also has very low surface recombination velocities, which means that it's less easily affected by surface states, less vulnerable to surface states. And since creating porosity, this is some porous gallium nitride, creates lots of surface, being immune to surface states is a really good thing. So porosification of gallium nitride gives us this new opportunity to change the material's properties of these nitride materials. We can think about changing a whole range of properties, refractive index, thermal electrical conductivity, and elastic constants. We can think about creating new quantum structures, and we can bring in the possibility of making pores, making little holes, and then filling them up with something else and creating new novel composites, combining gallium nitride with other materials. Now, I think my big focus today is actually going to be on engineering the refractive index, although within my group, we are working on engineering a number of different properties. But let's think about refractive index for now. So if we weren't going to engineer refractive index via the means of introducing porosity, how else might we do it? Well, we'd probably do it by creating an alloy of gallium nitride with one of the other nitrides, typically aluminium nitride. And the amount of change we can achieve in refractive index via that alloying is actually rather small. Whereas if we think about the range of porosity we can introduce into gallium nitride, we can get a much, much broader change in refractive index. And we can achieve potentially materials properties that would not be accessible via the alloying route. We can get forms of gallium nitride which, because they are porous, show us properties we can't otherwise achieve. So how, if we wish to be able to engineer refractive index, how are we going to create porosity in gallium nitride? Well, in silicon, electrochemical etching was used, and here we take a similar approach, an electrochemical approach. Our electrochemical process developed in Cambridge uses an oxalic acid as our electrolyte, as our etchant. We're using, our sample is the anode in an electrochemical circuit and platinum as our cathode. So we're going to have current flowing through the electrode, through the electrolyte and round this circuit. And what we're doing is applying a positive bias to our sample, and that's leading to hole injection into the N-type gallium nitride, and that those holes essentially catalyze oxidation of gallium nitride, and the oxide then dissolves in the electrolyte to leave behind pores. We can change the porosity by changing the bias we apply to the sample, or by changing the doping density. So this is one of the very early samples we porosified. So this is a process which can only happen when we have this electrochemical circuit completed. So undoped layers, like at the top here, basically don't etch because they show no conductivity. We can't flow current through them. And then more highly doped layers etch more, and rather low doped layers etch less. And that gives us one handle on controlling the porosity in our material. When you look at this image, which is a scanning electron microscope image, obviously we can see my porous layers and my non-porous layers. And you might think that we've cleaved a sample with these doped layers in it, and then etched that, and our etchant has penetrated here in through this cleaved surface that we're looking at. Now, the thing that's very unusual with our method for creating porosity is, in fact, that this material was etched as a whole wafer, and then we cleaved it to see the porosity later. And the etchant is actually accessing the doped layers through this undoped layer at the top, which appears completely untouched in the SEM image. And as we go through this talk, I'll explain how that can be. Okay, so what do we want to do with this material where we can now change the refractive index in a new way? Well, the first thing we wanted to do was create a distributed Bragg reflector, a mirror, essentially. At the time, we wanted those mirrors for single photon sources, but they're also a key component of resonant cavity light emitting diodes and vertical cavity surface emitting lasers, or VCSELs. Okay, so a distributed Bragg reflector is just a multi-layer of alternating layers of high and low refractive index material. Our high refractive index material is going to be gallium nitride, and our low refractive index material will be porous gallium nitride. And the period of that stack, we want to match it to a quarter of the wavelength of the light we wish to reflect, where it's the wavelength in the material, so normalized through the refractive index. And that then gives us constructive interference between light beams reflecting off each of these different interfaces, and gives us a strong reflection at that particular wavelength. Now, back in this diagram I had when I was talking about the band gap, we can talk about now, using this diagram, how we might create a distributed Bragg reflector just using pairs of semiconductors without any porosity involved at all. So if I was in the arsenide material system, I would use gallium arsenide and aluminium arsenide. They have roughly the same lattice constant. You can grow beautiful multi-layers just like this with very, very high reflectivities by growing an awful lot of layers. The trouble we have is that gallium nitride doesn't have the same lattice constant as aluminium nitride. The spacing between atoms in those two materials is different. And indium nitride, again, is different. So that means that this kind of lattice matched pair of binaries that we have in the arsenides that lets you do nice tidy growth to get beautiful multi-layers isn't really applicable in the nitrides. I'm just going to zoom in on that part of the diagram. So here I've got the lattice parameter against band gap, and we've got gallium nitride and aluminium nitride, which do have different lattice constants. But if we look at the alloy between aluminium nitride and indium nitride along this top line here, then there is a composition, indium aluminium nitride with 18% indium, which has the same lattice parameter, the same atomic spacing as gallium nitride. So from that, we should be able to make beautiful lattice matched DBRs. And indeed you can, actually. This is what goes wrong when I make distributed Bragg reflectors out of aluminium nitride and gallium nitride. Because the aluminium nitride is in tension on the gallium nitride, it tends to crack. And that means we get lots of variation in layer thickness in the stack. And you also generate lots of defects. You can see there's lots of little white lines in this picture, and those are extra defects in the crystal that tend to damage the performance of devices. But if we do the same thing with aluminium indium nitride, we have these beautiful uniform layers. So that totally works. It's a really good idea. I've done quite a lot of work on it myself. It's not the best solution though, because aluminium indium nitride actually has quite a similar refractive index to gallium nitride. So you need an awful lot of layers to get high reflectivities, because you need large index contrast really for strong reflections. Okay, but all of that is reliant on growing on this polar C plane. I said at the beginning of the talk that gallium nitride has this hexagonal crystal structure, but normally we are growing on this top face of the crystal if we imagine the crystal as a hexagonal prism, this kind of dark blue face. And we only then have to worry about the atomic spacing that I've got labeled as A here. The problem we had was that we were growing our devices on a different plane, what's called the A plane here. So this kind of rectangular cut through the hexagonal prism, a different face of the crystal structure. That has some advantages in terms of how the devices operate, but it now means we also have to worry about a second lattice constant, about the spacing of atoms along this direction I've got labeled as C. Now, the trouble is that I can also make lattice matched indium aluminium nitride to gallium nitride along the C direction. And I would do that by having 28% indium in my alloy. But what I can't have is lattice matching along both C and A simultaneously, because I can't grow in my crystal growth system material that has both 18% and 28% indium. That's possible. It has to be one or the other. So there are ways we might want to grow our crystals in gallium nitride where there is simply no option for a lattice matched material because of the special symmetry, or in fact lack of symmetry, of the gallium nitride crystal. So that's where we started thinking, right, okay, we need an alternative approach. We have these A-plane materials where we can't use any kind of lattice match pair. So instead, we're going to make porous gallium nitride. And we grew, in this case on A-plane GaN, these alternating layers of highly doped and undoped gallium nitride. And we etched those in the sample setup I showed you before. And this is the kind of distributed Bragg reflector that we can achieve. So we've got our non-porous GaN layers and then our porous GaN layers alternating up the stack with sort of nanoscale porosity. Now, that's not sort of new. We weren't the first people to do this, but there are some interesting differences between our process and the processes that have been used elsewhere. This idea, as far as I'm concerned, came out of a group at Yale, and their process is illustrated now at the bottom of the slide. So they start off again with one of these doped, undoped stacks. They then cover it in silicon dioxide, pattern the silicon dioxide into stripes. So windows with and without silicon dioxide in stripes across the surface. Use a deep reactive ion etch to create troughs or trenches in the material, and then the etchant accesses those dope layers from the side, from within these trenches. That's perfectly effective, but it is quite a complex multi-step process, and it is a kind of, it limits what you can do next with the etch structure you've made, because your device architectures are then going to have to work around this trench formation. But our process doesn't do any of this bit in the middle. We don't cover the surface with silicon dioxide. We don't make trenches. Our etching is happening from the top down. In this case, the etchant's going through these undoped layers, several of them you can see in my picture. Okay. Again, I'll come back to how that works in a second. I'm just going to show you a few of these completed DBRs on these unpatterned wafers. So here we've etched the vast majority of a 2-inch or 5-centimeter wafer. We've just got a region here where the wafer was held, where it's not etched, but you can see that we've got a lovely mirror, obviously reflecting the university logo. What else would you put in your mirror? Over the vast majority of this wafer surface, and it's completely unpatterned. It was just etched as grown as a full wafer. And we can change the layer thicknesses in our mirrors to change which wavelength they preferentially reflect. So we might have thinner layers to reflect blue light, or thicker layers and reflect green or yellow or even red light. And we can achieve reflectivities that are quite high, in excess of 90% across the board. And you can see that here for full wafers, as well as these little kind of test samples at the top. And I said that the etching happens through the top surface. And the thing that's rather remarkable is you might think that would completely damage and destroy the top surface. But what I've got here are atomic force microscopy images. They are atomically resolved in the Z direction. So these bands you can see are actually single and double atomic height steps in the gallium nitride. But before and after etching, we haven't really damaged the surface at all. There's a few bits of contamination after etching. We're better at cleaning the samples now, so that's less of an issue. But apart from that, it's really, there's nothing to see in terms of changes at the surface. Okay, so when we first kind of achieved these results, they were actually a bit of a mystery to us. We didn't really understand how we were managing to get these samples etched through these undoped layers with the etchant penetrating to reach the dope layers. I remember one of my graduate students going to a conference and somebody asked him exactly that question: how on earth can this work? And he said, it's magic. I'm afraid I'm here to say there isn't any magic, there is only science, and I'm hopefully now going to explain how we achieve this. So this is just another of these porous structures we've etched here with two distributed Bragg reflectors, top and bottom, above a quantum dot layer in the middle. And what I'm going to do is show you some transmission electron microscopy data where we've made a very, very thin foil that contains just one of these porous layers. And we've taken that sheet of material out, and then we're going to look at it in plan view. So this is meant to be an eye looking down on the top of my sample. And what we're looking through is this thin lamella that we've cut out from this gallium nitride stack. And this is what we see, not now from the side as here, but from the top. We see these little black dots, which are essentially little holes in the gallium nitride, from which the pores, which you here see in mid-gray, emanate. And the kind of remaining gallium nitride, the struts between the pores, are these pale gray or white lines. So it almost looks like the petals of a flower. And what we have is the porosity emanating from these dark dots out in a sort of circular fashion until the porosity arising from different dark dots bumps into one another, and then we have a boundary between the two, making a sort of domain. So I guess the next question is, well, what these little dark dots, these little holes or pipes going through the material, where are they coming from? So here's another example of the sorts of structures we see. But again, the same pattern. Sometimes we see very branched structures, but again, always emanating out from this central dark dot or hole. What we need to do now is zoom in on that hole. Now, you'll hopefully remember that right at the beginning, I stressed that we have defects, mistakes in the crystal that run through all these nitride films that are grown on unlike substrates. Here we're growing on sapphire. Those defects are what we call dislocations. They're a line defect, a line of like improper bonding in the crystal. And if we zoom in on one of these little dark dots, there is a hole in our sample, we can identify that there was a dislocation at the location of that hole. Now, I hope you can see on your screens, these are now in this top right-hand corner, atomically resolved images. And what we've done is drawn what we call a Burger's circuit around the defect or around the dislocation. A Burger's circuit is just a circuit in the crystal where we're taking steps which are like from one atom to the next along the periodic structure of the crystal. And if we did that in a perfect crystal, we'd be able to go round and it would close. And if we take that closed circuit and take the same number of steps around a defect, around a dislocation, the circuit doesn't close. So this hexagonal ring here you're seeing is my Burger's circuit. It would close with the number of steps we've taken if we were in the perfect crystal, but actually it doesn't quite close. And we have this lack of closure vector, this displacement where it ought to be closed and isn't, and that's expressive of the fact that there's a defect that was running down through this hole. So the defects have actually turned into pipes through which the etchant can run. Sometimes we can just about still see the atomic structure of the defect. So here we've got one of these holes from which the pores seem to emanate, but rather than there being a completely through the sample hole, there's actually just a thin layer of material left. And then we can see where the bonding is wrong down this line of defect in the crystal in this atomic resolution image. And we can identify the nature, the crystallographic nature of the defect. I have to be honest and say sometimes we find a load of holes and we can't find the defect. And in that case, we don't know what's going on. But the vast majority of the porosity is coming from these defects, which become little tiny nano pipelines through our crystal and let the etchant access the dope layers. So if we now look at how the etching of the porous GAN progresses with time, I've got here one of these doped, undoped multi-layers. And if we look at it very early on in the etching, this is like we've stopped the etching and then cleave the sample, have a look what's going on. We can just see we've just started etching the top layer. If we double how long we etch for, we finish etching the top layer and start on the second layer. If we extend the time further, we can etch through 4 or 5 layers. And then only at long times do we really get down to the bottom layers in this stack that we are etching. So that then allows us to summarize what's going on with the etching mechanism. If we start off with these defects, these dislocations running through this material, which consists of doped and undoped layers, when we turn on the bias, we essentially first open a pipeline at the defect, and then from there the etch heads outwards through the conductive dope layer until that layer's all etched, and then we open the pipeline to the next layer, etch the next layer, and so the etching proceeds through the defect pipeline all the way through the stack. I'm going to show you this now in a kind of more three-dimensional way, except that in this case we have, rather than just a little tiny defect pipeline, we've actually got a really great big pit, also related to a defect, in the sample. Now I'm showing you this because it really kind of exemplifies some of the mechanism we've been talking about, but I have to say this is not a good bit of material. This is a piece of material where we have these large pits because we've got something wrong during the crystal growth. Probably the growth temperature was slightly off from where it should have been, but the pits give us something to sort of focus on in the microscopy. And what I'm going to do now, I probably need to switch off my pointer for a second. When I run a video, what we're looking at here is an SEM image, a scanning electron microscopy image, but it's taken in a focused ion beam microscope. And when I run the video, I'm going to use the focused ion beam to kind of scrape away the surface gallium nitride and see the porosity beneath. And then we'll scrape away the first porous layer and see a non-porous layer, and then scrape away again and see the next porous layer. And we can actually mill down through all these layers and reveal the structure that's formed. So here we go, milling down through the layers. We're forming big droplets of gallium because of this milling process, but you can see there's a non-porous layer. Here's another porous layer appearing. We're milling down through that to another non-porous layer, back into the next porous layer, and onward down through the crystal. It gets more and more sort of spoilt by these large gallium droplets. So we only managed to mill here down through about 5 layers. And then we can take those images which were taken at a slight angle, process them so it's as if we're looking down straight from the top, and look at the porous layer here in the SEM. We're seeing some quite similar features to what we saw in the TEM. It's a bit damaged by the whole focused ion beam milling process. But we've got these pipelines, which are the ones we associate with the dislocations. We see the porosity emanating from them, and we see these same borders that we've noticed between porous domains before. I have my pointer back, I think. And then we have this great big hole in the surface, and we immediately notice that that's made a bigger domain of porosity than the other dislocations that we've seen elsewhere. And we can pull out these domains quite nicely, and just kind of zooming in on them there, emphasizing that for this first porous layer up in this area, the etchings really happen via this dislocation pathway. But if we go down to the 5th porous layer, it looks quite different. Our milling has got a bit like a bowl shape here. So we've kind of destroyed the middle of the porous layer before we've really accessed the edge of it. But if we look at that same region I was looking at a moment ago, we can now see that the porosity is really all kind of heading in one direction, that it's aligned, and the porosity is all emanating radially from this huge big pit we've got in the center, rather than for those individual dislocation pipelines. So our etching mechanism has actually gone a bit wrong at this V pit. To start with, we have etching happening down the dislocation course, but also via the means of the V pit. But the etching can access far down into the structure from the V pit because it's just straight there. It hasn't got to form a pipeline or anything. It can just dig right in. So as we continue to etch, the etching via the dislocations may be happening quite slowly, but there's this kind of short circuit route from the etchants to the lower layers. So layers further down are really dominated by the etching via the V-pit, which means that by the time we get into the really deepest layers of the structure, our entire morphology is going to be dominated by etching from this large feature that's not really intended to be in our sample. Now, that's a nice bit of microscopy. It's a nice kind of science story, but it also revealed some things to us that were surprising about the optical properties of this material. What I'm showing you now is a polarized light microscopy image of this sample with these great big pits in. And we can see, looking in polarized light microscopy, these Maltese cross structures, sort of in blue and purple, these crosses, each with a dark center. And if we rotate the angle of our polarized light, we can cause those crosses to rotate in our field of view. Now, what are we doing here? Polarized light microscopy. It's a way of looking at birefringent materials, materials whose refractive index is different along two perpendicular directions. Essentially, in a classic polarized light microscopy experiment, which would be done in transmission, we have polarized light coming into our sample. Because of the birefringence, because of the difference in refractive index between the two different optical axes, the axis of that polarized light is rotated somewhat via its passage through the material. And that means that when the light meets the analyzer, it would be blocked if there had been no rotation, but because it has been somewhat rotated, we now see light actually being able to come through, and we image those regions where there is anisotropy as being bright in our polarized light micrograph. Okay, so the fact that we can see features in polarized light microscopy means we now have a birefringent material. And that links back to that structure we were just seeing, that structure with the radiating pores from that big central pit. Because the refractive index will be different along the pores and across the pores. But because we have a radial structure, the anisotropy will depend on where we are around that circle, with the fast direction, i.e. the low refractive index, being differently oriented, being basically circumferential always as we go around the circle. If my slide will move on. So when we look at that in the polarized light microscope, what do we expect to see? Well, I'm just going to take kind of 4 exemplar directions here and consider what happens to them if we've got light along the direction I'm showing on the slide, polarized. So the polarized light experiences the refractive indices differently depending on what angle it finds itself to them. We'll have a low refractive index, we think, along the pores and a high refractive index across the pores. But if we look at this orientation down here, where the direction of the polarization is parallel to the direction of the pores, the light only experiences one of those refractive indices. So that means that because there is no component of the light resolved along the second refractive index, there'll be no rotation of the polarization. Whereas at an angle, this will work. So, so that means that if we bring in the analyzer, this region will seem dark because the light's rotation doesn't change, okay? Whereas if we have an angle like this, where we're sampling both of our 2 refractive indices with our polarized light, then we'll see a large phase change and the material will appear bright. And at angles which are kind of a bit closer to the light being parallel to the pores, we'll see a little bit of phase change and some light passing through, but not very much. So that means if we then think about what we expect to see, we'll have regions where the light is either perfectly parallel to the pores or perfectly perpendicular to the pores, where we're only sampling one of the two refractive indices, where the material appears dark. And then as we get closer and closer to the point where we have that maximum phase change, the whole thing will appear the brightest. And that gives us this Maltese cross appearance from this radial structure that we accidentally created. Is this actually relevant at all, except in these structures where we've accidentally created these great big pits, which you can see here in the SEM and here also in the AFM? Because as I say, this isn't good material. Well, what we needed to do was probe more deeply through our real device structures. And we've done that using some transmission electron microscopy experiments, because what we wanted to find out was whether these large fields were present in our real device structures. So what we've done to probe that in the TEM, rather than using the fib that I showed earlier, when we make a TEM sample, we need a really thin foil of material. And we make that using an ion beam milling technique, where we typically have two ion guns coming from opposite angles, milling away at the material to make a thin region here at the center of the material. And we'd normally just look at that in the electron microscope, and we'd maybe have thin enough material to see the porosity just at this edge here, for example. And if we then come in with the ion gun again, having turned the sample over, we can access deeper layers by milling further into the structure. So if I move the ion gun, now the region that's thin is going to be this second layer here. And we can take this approach and actually sample all the way down through a multi-layer, taking the material and milling away more and more, and then returning the sample to the transmission electron microscope. So the whole process, we start off just making a normal plan view TEM sample. We look at it in the TEM. Then we do this extra ion milling step from the front side. We put it back in the TEM and see the next layer down, and then keep on repeating. Fabian, who's the postdoc who did this work, says he did this 23 times, this whole cycle. That's why there is coffee in the cycle as well. Fabian reckons this is him during this experiment, because we had the microscope available basically for a 24-hour period and kept going round and round and round and round the cycle. And it was very hard work. And then he eventually went home to bed and had a good long rest thereafter. But what that allowed us to do, and I'm not going to talk about all the many layers we see, is sample the layers both near the sample surface and very deep below the sample surface. And what we saw was that even where we have the etching only happening via our dislocations, far below the sample surface, we do have these very, very large fields where the porosity emanates from one central defect out for microns of distance. And the size of these etching fields is determined by how far through we are through the stack, with the average diameter of an etching field getting larger and larger the more deep we go. So yes, this question of like radial birefringence is relevant to our standard samples. The other thing is that having discovered this birefringence effect, we realized we could control it. Now I have to say here, we're swapping from our dislocation-based approach to etching these samples into an approach much more similar to the original way that porous gallium nitride was made, with lithographic steps. We've put down protective silicon nitride on the surface. We use a reactive ion etch to take away a big trench of material, and then our porosification is going to happen from those trench sidewalls out rather than through defects. But the idea here was that by etching in this radial fashion, we could control the direction of the pores. So when we put a sample like that into the polarized light microscope, well, to start with, this is just a standard light microscopy image. And you can see that we've not etched all the way through our material. So we've got our trenches here. On the edge, we've got successful etching. We've got a little bit of etching that goes up to about 20 microns in, and then we've got an unetched region at the center. And that kind of illustrates the limitation of this kind of radial approach. We've also got one place here where there was a hole in the silicon nitride where it's etched from the top, which is why there's a bright spot there. Taking that into the polarized light way of imaging, we can see that we have these regions right next to that sidewall with this very, very bright contrast in the polarized light microscopy. And we have indeed, we think, and I'll show you how we know, managed to align the pores. We can also see one Maltese cross structure, which is radial etching, in this case, driven by the hole in our silicon nitride rather than necessarily by a big pit. And if we rotate our sample, we can actually eliminate the contrast from this porous material, because we can align the direction of the porosity with the direction of the polarized light, and then we have no rotation of the direction of polarization anymore. We still see, however, the Maltese cross, because there the porosity is radial, so there's always some material which is not aligned so well with the polarized light. We just produced some models of this using COMSOL, finite element type modeling. So we've modeled this as being cylindrical pores in layers running through the material. And we can use that structure and model our expected reflectivity curve against wavelength. And then we can think about the polarization of the reflectivity. So here is our model data, assuming these aligned cylindrical pores. And we can see that as we change the polarization of the incoming light, what we actually see is we're losing part of the stop band as we rotate the polarization, and we're narrowing down the stop band. And if we do exactly the same thing experimentally, the data is maybe not quite as clean as the beautiful model, but we see exactly that. We lose this part of the stop band as we go from the 90 degrees to the 0 degree polarization. So essentially what we have is a polarization dependent mirror, but only in this fairly narrow range in the short wavelength regime. The modeling isn't completely able to reproduce this rotation of the polarized light that we see in the polarized light microscopy though, but it gives us an idea that we really are starting to understand these structures. Just to show you, well, do we really have aligned pores? I'm going to show you another microscopy technique. I'm into microscopy. I suspect this is unusual for this audience. Another microscopy technique that we can use to show that we have these aligned pores. This is again in the focused ion beam microscope, and we've created a sort of big fat maser out of our DBR here with these aligned pores. And what we're going to do is take a SEM image and then use the ion beam to slice off some of the material, a bit like slicing like a bar cake or a loaf cake. And then we're going to take another SEM image. So I'll just show you how the experiment looks as it runs. So we slice away an image and slice an image, and we keep going in depth into this big lump of material. And if you look carefully, you can follow pores that penetrate into the material, and then some will vanish and new ones will appear. What we can do with the data set that we get from that experiment is essentially reconstruct the full three-dimensional structure of the porous distributed Bragg reflector. What I'm showing here is just one layer now looked at from the top rather than in cross-section from the side. And this isn't a real image. This is an image which is made up from all the sections, and then we've digitally cut it out to look at a single layer of the distributed Bragg reflector. And we can see we don't have the perfect aligned cylindrical pores of the model, but we do have a very strong preference for alignment of the pores in a particular direction. And this is the kind of full three-dimensional reconstruction of that data. You can see these multiple slightly branching porous layers, and we can extract any one of them, and they're all branched but with a predominant direction in which the porosity lies. And that's what's leading to the birefringence that we see, that anisotropy of the porosity. Okay, so what can we do with this? Well, we can make a mirror. Yeah, that was what we were trying to do in the first place. And we can introduce that mirror, for example, into a light emitting diode. Let's get my pointer back. So this is a very, very simple light emitting diode structure where we've just put the porous distributed Bragg reflector under the light emitting diode. Now, because we can etch the distributed Bragg reflectors at the wafer scale, we can essentially just treat them completely like a substrate. just as if we had any other gallium nitride substrate we wanted to put into our growth reactor. And then we can grow our structure of the LED on top with P and N type layers and quantum wells. And we can then fabricate it in entirely the normal fashion. We grew 2 LEDs simultaneously, and we fabricated a LED structures in exactly the same way. And what we can see is that when we introduce the porous layer, we increase, for the same drive current, the amount of light we're getting out of the device. And that's simply because we're reflecting out light that would otherwise be lost because it's emitted from the quantum wells down into the substrate. And we can see that if we work out an efficiency curve, that increase in light extraction is increasing the efficiency of our device, which is exactly what we'd expect it to do. We can also bring these porous distributed Bragg reflectors into more exotic devices. So as I say, when we started, what we wanted to make was a single photon source, and we needed DBRs for that. So this is one such single photon emitting device. So here we've got a quantum dot layer sandwiched between 2 porous gallium nitride distributed Bragg reflectors. And we milled that then into these micro pillar structures, which ideally would be beautiful cavities. They aren't as beautiful as we might like, particularly at the stage when this experiment was done. We hadn't really got the processing under control. So they're somewhat surrounded by what you might call like grass of gallium nitride, because the etching process to make the pillar has been disturbed by the porosity. And we've done some optimization to reduce that effect since. But this is the device we actually did quite a lot of the optical work on. So these are now data taken at low temperatures, and we're looking at single quantum dot emission from in these devices. And we can get very, very high numbers of counts per second out of a quantum dot because of the extraction efficiency we're achieving using these distributed Bragg reflectors. And then we can do a Hanby, Brown and Twist experiment, which is how we test a single photon emitter. I'm not going to go into that in any detail, just to say that pragmatically, what we're looking for is a pulse train with a dip in it at time 0, okay? And that dip indicates that we have a single photon emitter. And what we want is for the dip to be as low as possible relative to the surrounding peaks. That would be really pure single photon emission. And using these very bright single photon sources that we've achieved using the porous distributed Bragg reflectors, we've been able to tune the excitation conditions to get the purest single photon stream that's ever been reported for indium gallium nitride. So this is the thing we, I guess, originally wanted to do with these distributed Bragg reflectors, and then kind of got distracted by making porous GaN, to be honest. But we can see it's really working well here as a way of making a brighter and a better device. Okay, just before I finish, a sort of moment of something completely different. I said at the beginning that we could also put other materials into the pores. So here's a very simple example of doing that. So here we have the porosity at the surface without a non-porous cap on top. And we're just going to drop some ethanol into that. Sorry, it might be a bit noisy even at your end. It's not a very good video. So here comes a pipette. We're going to drip in some ethanol. What we see once the video sorts itself out is that the ethanol has sunk right into the pores. It spreads out and sinks in. And then as it evaporates, you'll see the kind of yellow spot we've got currently shrinking, and we see fringing developing as the refractive index and the volume of ethanol infiltrated into the device changes. And he'll do it once more here. And there we are. We can see the ethanol spreading out and really sinking into the device. And we're almost going to normalize the refractive index to be the same as the surrounding material. And then as the ethanol evaporates, we'll return back to having a different refractive index, which is the refractive index of the porous gallium nitride. Hopefully. So we can definitely get solvents into the pores, but they then just evaporate, and that maybe isn't very interesting. So the next thing we wanted to develop was the ability to get another interesting optoelectronic material into the pores. And the material we chose was a perovskite material, one of these lead halide perovskites that's really exciting for new solar cell architectures. Now, the problem with these lead halide perovskites is they're really unstable to air. And we wondered what would happen if we infiltrated them into an optically active porous matrix. So we developed a process for doing that, where we soak the porous gallium nitride in the precursor solutions for the perovskite material. And then we actually have the reaction goes on that forms the perovskite within the pores. We're using them almost like little test tubes. And if we look at that again in the transmission electron microscope, we can use EDX imaging, which is a composition sensitive technique. And we can see here the bright areas are where the pores are, where there's less gallium. And in those same areas, we have little dots of lead and bromine, which is how we're identifying our lead halide perovskite. So we can show that we really have achieved this infiltration into the pores. And when we do that, it's really great in terms of the photoluminescence from these materials. Because normally, if you just leave these materials without encapsulation, like the example I've got here shown on glass, over a period of, say, 10 days, the photoluminescence completely degrades and you end up with almost no light coming out from your samples. But here, and the same thing if we just put it on a planar GaN surface, again, the photoluminescence degrades. But if we have material that's that's encapsulated in our porous GaN, although we do see some degradation, actually the degradation is only that where the same as it would be as if we'd properly encapsulated it as soon as it was grown in a little glass box and never exposed it to ambient. It doesn't degrade very much at all. And in fact, we left these samples for a year and find that they were still showing perovskite luminescence over the course of a year, which is almost unheard of for these types of lead halide perovskites. We could also see that by putting the perovskite into different size pores in gallium nitride, we could see different wavelengths of the luminescence. And that's because we're templating the formation of different size nanocrystals using the pores. Okay, so summing up some stuff we've done with porous GaN. Basically, we can make unique nanostructures, these beautiful flower-like structures, through this electrochemical etching process. That alters the material's properties, it changes the refractive index, it introduces a new degree of birefringence. It also provides us with novel substrates on which we can do device overgrowth, substrates which are both mirrors, intact and complete mirrors, but also which are perfectly good substrates for our growth. It lets us develop new device architectures, like for our single photon sources. And it lets us create these composites of gallium nitride with other materials, which, so far we've shown it does interesting things to the perovskites, but in the future we can think about composites which are going to combine the unique properties of gallium nitride with that of other materials. Could be magnetic materials or ferroelectric materials. There's all sorts of possibilities there. Okay, thank you all very much for listening.
And thank you very much for a wonderful presentation, Rachel. It's really exciting to see the work that's coming through and coming up. I know we are at the time of day where we had it scheduled to finish, but can we keep you to ask a few questions?
Yeah, I'm sorry, I think I was a bit long. I didn't have a clock, which was foolish of me.
No. We started, my introduction does run out a bit as well, so I will be happy. But I see there's Gally Suito, who has his hand up in the audience. Gally, can you unmute yourself and come on screen to ask your question?
Thank you. Thank you very much, Professor Rachel Oliver. It was really amazing project you had. I'm a PhD candidate at McGill, working on heteroepitaxy of 351 silicon for silicon photonics. When I was undergraduate at Nagoya University, everybody doing nitride, and I was involved in nitride-based DBR as well. So I know the pain of having 40, 50 periodic stacks.
It was on forever. So yeah,
yeah. So I know the pain.
Ages.
Yes, so it's amazing. Also here at McGill, we're also exploring DBR, trying to make indium phosphide air, etc., etc. But of course, obviously, for a practical electronic, these air composite materials are not practical due to mechanical instability. So sure, this porous nitride is really amazing. I'm really surprised with the results as well. So one thing I'm wondering is how is the mechanical stability of this porous nitride? Since you also have optoelectronic devices fabricated, have you also checked like is like the brittleness, etc., and how it the ability to be integrated to others devices?
Yeah, so we've actually done some measurements on the mechanical properties, and the porous material has a much lower elastic constant than the normal gallium nitride. It's much squishier, like a sponge. Yeah. And if you go to too high an etching voltage and make the pores really large, then it does become quite brittle and quite, I would say, friable, kind of crumbly. But up to about 60% porosity, it's mechanically very stable, and we don't see any particular problems with mechanical stability. We can actually, so we've done experiments where we deliberately make it very, very porous intentionally, and then you can actually create layers as separation layers on purpose. So if you want to separate your gallium nitride from its substrate to transfer it to another substrate, for example, you can deliberately make a weak interface and then, like almost like graphene, peel it off with Scotch tape, that kind of approach. Maybe not very manufacturable, but you can imagine it as a kind of way forward for separating layers. But yeah, up to about 60% porosity, you're fine. If you get to the sort of 80-90% porosity approach, then yeah, it's pretty yes, delicate at that point. But for moderate porosities, it's squishier than normal GaN, but basically pretty stable. And we haven't seen any issues in terms of device degradation as yet. But obviously these devices are pretty new, so we haven't got the kind of long-term life testing you might have for standard gallium nitride devices.
Thank you very much. One more question. Is it okay, Matt?
Yeah, go for it.
So yeah, the porous nitride with other materials, very interesting. Can you comment on the wavelength shift?
In terms of the so the wavelength shift we saw was in the perovskites. And what we think is happening, and the calculations we have sort of bear it out, is that literally we're just making smaller quantum dots in the smaller pores, and that then we change the quantization energies. It's also worth saying that we have done some work looking at indium gallium nitride and making like quantum structures in the porous material itself as well, and we see wavelength shifts there as well, but they're really difficult to interpret because we're not sure whether we're also changing both the strain and the composition of the material, and all those things affect the wavelength. So sort of seeing wavelength shifts in the nitride itself, we don't quite know what's going on.
Thank you very much. The dot size looks interesting. Thank you. Thank you, Professor Rachel.
Thank you.
Wonderful. There's a question which has come up in the chat, Rachel.
I'll see if I can find it. Give me a sec. Oh, yeah. Did we perform an annealing on the porous GaN, and how does it affect the DBR and the LED properties? We didn't perform a deliberate anneal, but we did grow structures on top, which means we held the DBR at temperature. And you have to be quite careful about how you start the growth. If you hold it at temperature too long without starting the growth, you start to see the pores getting bigger and kind of the porous layers starting to run into one another. And that degrades the properties of the DBR. So you can't leave it annealing at very high temperatures. And this is like 1000 to 1100 degrees C, so it's properly hot for long periods of time, unless you grow more GaN on top to stabilize the structure. But you can, as long as you start growing soon enough, you can keep it stable. But yeah, I wouldn't trust these materials at very high temperatures, except in a growth atmosphere. They might be quite all right at kind of 700, 800 degrees C, which is already pretty hot, but not at 1000, where the gallium nitride really does start to break down. Hopefully that answered the question.
Thank you. That's good for you, Busalari. Do let us know in the chat.
Thanks.
We have a thank you. I have one last question, if I may. Maybe you two, but we'll start with one. There was a terminology which you introduced earlier, the Burgers holes.
The Burgers method, yeah. I shall see if I can go backwards to that.
Yeah, would they be like in the earlier studies where they were using the process in the DRE to access the layers to be able to do the wet chemical etching? Are they kind of analogous in that way to what was being done in these earlier studies, of these kind of routes into the porous layers to do the etching? Is that what they represent? I'm not familiar with the terminology, so if you could just help clarify on that.
Yeah, so the Burgers vector, the Burgers circuit is just a way of identifying a particular sort of defect, okay?
Okay.
The defect in question is a dislocation. Yeah, so sorry, I should probably have explained these better. So the simplest type of dislocation, and there's a few, okay, but the simple ones, if you imagine a crystal as being like just loads of layers of atoms that are like the pages in a book, yeah, and then you imagine like sticking in half an extra page or maybe a bookmark into a book, which is an extra layer of atoms. And then because it's only a half a page, it distorts all the crystal structure around it because it's kind of pushing the other layers out of the way. That's what a dislocation actually is. It's an extra half plane of atoms. There's other types, but the kind of basic one, okay? So the reason the bonding's distorted is you've got half an extra layer of atoms in. And the reason that the Burgers circuit doesn't meet up is that compared to the perfect crystal, on one side of the circuit, you've got this extra half a layer, and then the other side you haven't. So the Burgers circuit is just a way of identifying where this mistake in the crystal with this extra half a layer of atoms is. At that place where you have the extra half a layer of atoms, the bonding's distorted. So this image here, you can see that in the perfect crystal, we've got these neat like hexagonal rings of atoms. These are just the gallium atoms in the crystal. But if we look in this defected region, that kind of neat hexagonal ring structure breaks down and we see larger and smaller rings of atoms. And that's because the bonding's all gone wrong because of introducing this extra half plane. Excuse me. And that point, because the bonding is not appropriate for the crystal, the bonds are weaker, which means the etchant can attack them. And we also think that any impurities tend to segregate to the region near that problem in the crystal, and that makes that region like really susceptible to the etch. So there's no hole there to start with, but when the etch comes along, because the bonding's weak and because there's a little tiny bit of conductivity, it etches straight down that mistake of the crystal and it kind of self-forms a pipe. So if we look at the kind of traditional way of making these things, they've like dug big holes. And what this way of doing is taking a pre-existing problem in the crystal and like letting the etch select for it, and the etch makes its own route then down to the dope layer. And then when it's finished etching that dope layer, it then goes further down that same pipe down to the next dope layer. So it's really interesting. It's something I'm really sort of fascinated by, because dislocations, these defects, have been like the big problem that everybody worries about in gallium nitride. And oh, how on earth do you make decent devices from these materials that are full of defects? But actually what we're doing is turning them into a useful part of the process for making our porous materials.
That's wonderful. And actually that kind of leads me on to the next question. In where you've spun out the company, is that type of process really, I guess, the special thing which is selling products at the moment, or is it something else?
So yes, and then again, no. Okay, so that process is absolutely the foundation of the company, and it's absolutely the thing that the company is using to make our porous nitride samples. When we originally spun out the company, we thought we were going to sell essentially mirrors and devices with mirrors, because that was the thing we were making by our beautiful process. And the company does sell some mirrors. But the thing that is getting people excited about the company is that we've used that process to develop some mechanically compliant nitride layers, which we're then using to grow red LEDs on top of. Now, you don't think of the nitrides as being a red LED material because you think indium phosphide. So Gali can probably tell me about indium phosphide for red emitters. But as you make indium phosphide devices smaller and smaller, they get less and less efficient because they're really sensitive to surface states, whereas gallium nitride is not really very sensitive to surface states. So the disadvantage of the nitrides for the red kind of goes away somewhat at very, very small device sizes, because the phosphides are no longer that kind of powerful a force. So because people are currently really interested in tiny micro LEDs for augmented reality and virtual reality headsets, and really, really mini micro displays with LED sizes on the few micron scale, growing red nitride devices has suddenly become a really kind of hot area. And it turns out that we can improve the growth of red emitting nitrides a lot by incorporating these porous underlayers, which essentially make the substrate compliant and allow us to get more indium incorporated, because they're kind of take the porous layer is kind of taking up some of the strain in the structure. So that's really where the company is going, which is not not at all what I expected when we founded the company. It's not what we were aiming for, but I do some talks, particularly for like the commercialization service in Cambridge, talking about like the whole spin out experience. And something I say is, you think you started out with a brilliant idea and sometimes it goes off on a massive tangent, but if that's where like the demand for the device is taking you and the market's interested with a company, that's fine. There's no kind of right answer to what the company should do. So that's been quite an adventure.
That's wonderful. Thank you for sharing that adventure. And actually, you got a question from over the pond, I think. Stefan was writing to me saying he had a question. So Stefan, if you want to...
Hi, Rachel. So I'm from University of Southampton, and we mainly work with, I mainly work with silicon nitride in the near infrared. So really, my question is, have you thought about using this method of, pushing towards near infrared, like indium phosphide or gallium arsenide sort of devices? Because I'm probably thinking you probably can apply the same sort of, style of effect on creating different lasers, with different structures, obviously.
Yeah, so it's a really interesting question. So do you mean, could we use the same etching approach in these other materials? Is that
so just changing that, making these tunable refractive indexes layers. Because at the moment, for instance, what we do is, so imagine I have a 3.5 laser that is like monolithically grown on silicon. So for instance, obviously, if you go from silicon or silicon nitride to 3.5 material like indium phosphide, you're going to have a lot of reflection going on there. So what we do at the moment is we have like arc layers or anti-reflective rails, which we just tune the refractive index of silicon nitride. So we made like a step-based transition, essentially. But this takes like a lot of different processing steps, to be honest, and because you kind of need multiple refractive index layers, so you need all the time you need to like redeposit them. So that's another mask you add to the process. Which already, if you want to make a device like this, you need like 70 masks or something. It's just stupid.
So basically, in terms of the basics of perovskification, it has been done in the arsenides. I'm not sure about in the phosphides, but I'm pretty sure it's applicable to the phosphides. I just can't bring a paper to mind, if you know what I mean. So in terms of the original method where you would maybe etch a trench and then have the electrochemical perovskification heading laterally, I'm pretty sure that's applicable to any material you happen to try it in. Okay. In terms of what we're doing about working down the defects, okay, I guess initially I didn't necessarily think of it for the arsenides because you think of the arsenides as being a much more perfect material with very few defects. But for the samples that are grown on silicon, they actually do have threading dislocations, very much like gallium nitride, and people spend a lot of heartache trying to control those dislocations or get rid of them. Okay. And it is possible, although I haven't proved it, that the same mechanism would be applicable there. It will depend a little bit on the structure of the dislocation and also on the gettering or otherwise of impurity to the dislocation. But I think it would be a thing worth trying to see if the defect mediated etching mechanism we have here in the nitrides applies in other 3.5s. I can't see any kind of absolute reason why it wouldn't. But as I say, there's going to be some sensitivity to the exact structure of the defects. And it might also be quite funky because one of the things that goes wrong in some of the 3.5 on silicon type devices is to do with the motion of the dislocations. And actually, once you'd etch them into tiny nanopipes, they probably wouldn't move at all. They'd be stuck. So it might actually overcome another problem as well. So I think actually it could be a really interesting thing to try, but I don't have any data that sort of shows it works. But yeah, it would be a fun thing to play with.
Well, I heard funky, thank you. I heard funky, I heard fun, I heard worth a try. So there you go, open up a route of communication. And
absolutely, yeah, feel free to drop me an email about it. It's the sort of thing that sounds much like it might be amusing.
Thank you for your availability, Rachel, and for taking the extra time. We have overrun by 20 minutes, so I for the discussion, and I do appreciate everyone that's chimed in for that as well. I didn't even check, Ajay, was there anything in the room? Anyone you wanted to react?
No question from the room, but very neat presentations.
It's lovely to speak to you all.
Yeah, thanks for the wonderful presentation.
great if everyone can join me again in clapping virtually or in person. Professor Rachel Oliver, what a wonderful hour and a bit to have you with us, and we really appreciate the time you've taken out of your early evening in the UK to join us today. So thank you everyone, and see you again next time.
Thank you very much for having me. Bye-bye.
Yeah, bye.